Good afternoon. We resume our lecture on Six Sigma, and in particular, today's lecture is the fourth lecture in this set of the three different other lectures that I had on statistical process control. This is a very important topic, the one that we are going to be discussing today. This is called process capability. As you see in the slide there, the title slide, it talks about the capability of the process to be able to satisfy customer requirements. That's what basically this is. Now, if you look at the diagram that I have on the paper here, here's a process, and you can actually see the process. It's a box for us, and it's influenced by various factors, A, B, C. These are process control factors. Then, of course, we've got noise factors, which we are not controlling, but they are nevertheless there. They are part of the environment, which is causing the variation in the process. As a result, what you'll find is when you look at the output does not turn out to be a single value. The output itself is also variable. The process quality characteristic that you see there, the output actually shows quite a bit of variation, and that sometimes goes even beyond the limits that is specified by the customer. For example, this is the upper spec limit, USL, and this is the lower spec limit. That is the lowest value of quality that the customer is willing to live with. In between, of course, the part is okay. That part is okay. So if my production is all within these two limits there, then there is no problem with the process. But if it turns out, if it has got variations like this, when part of the output falls below the lower control limit, lower specification limit, or part of it falls above the beyond the upper specification limit, I say that the process is not capable of satisfying the customer 100% of the time. And this can happen not only because of variations in the noise factors, which you are not controlling, but it's also very possible that the process variables themselves, they also have some variation. So each of the process variables that you set at the set point, they may also have some variation. And because of that, these variations, they impact the process, and the result is you got some inflated variation in the output of the process itself. Process capability, this phrase is the measure of how well a particular process is able to satisfy or fall within the upper and lower specification limits. That's what really process capability is. Let's move into the lecture here. We realize and we know by this time that if you're talking about process improvement generally moves in steps. You know, in the Six Sigma framework, we of course have DMAC. DMAC is define, measure, analyze, improve, and then control. DMAC. Any problem solving procedure generally moves along these paths there. And the same thing I have for process improvement. I have measurement, then I have analysis, then I have control, then I've got the improvement done, and then of course innovation. You need innovation, otherwise you'd be stuck wherever you are. If you look at the steps that this is following, I have control and improve. That will be like, for example, if you've taken care of measurement and analysis, then you'll be controlling, and you'll try to improve to a higher level of quality. And to get there, generally the breakthrough procedure would be through innovation, and that would come through a process like design of experiments, for example. And again, you'd stabilize with your PDCA cycle, you'll stabilize around a certain level of quality. From there, you might like to compete a bit better, and you'd like to improve the process, and that you do. So this in fact goes on and on and on. It moves like a cycle. You have control, then improve, innovate, then again control, improve, innovate, and so on. That's how you'll be moving along. One of the reasons for doing this is generally to try to improve the process capability of any process that you're operating. If you're not doing it, your competition for sure is doing it. This competition, generally a good competitor, he benchmarks his products against the best that is there in the marketplace, and he tries to offer value. Value is what he offers for the price that he offers it. He will always try to improve upon the value that he's offering. And he'd try his best to try to outcompete other people. Let's try to get a visual picture of this notion of process capability. As I showed you earlier, a process will have a lot of variations coming in because of a variety of reasons. Some may be due to the control factors, which themselves are, although they are set at set points, they may not exactly stay there. As a result of that, you'll end up with some variation that is introduced by the process control variables themselves, because those themselves, they do not hold on to their set points. Then, of course, in addition, you got other factors that you're not controlling, and these are the noise factors. As we saw in the diagram, there is a noise factor here, and there is a noise factor here, and these are operating independent of whatever else is going on there. So they will also be active, and they will also try to impact the variability of the process itself. When that happens, returning to the slide there, the screen here, we end up with what we call some inherent variability of the process. Okay, we realize that every process is going to be variable. Unfortunately, what happens, as customers, we have our specific requirements. And these specific requirements are communicated, and they're actually captured by market research, and those would be called what we call specification limits. This is kind of the tolerance band within which the product would be treated to be okay, and if it goes beyond that tolerance band, the product would be considered to be off spec. And that's exactly what we see there when we look at the output there. These red regions, these two red regions, one is to the left, the other is to the right. These two indicate basically the different points which are either below the specification limit or above the specification limit. These products, if they are offered in the marketplace, no one is going to buy them because they are beyond the specification limit. That's something you've got to remember. Therefore, it becomes very important for us to worry about a process that is delivering products that fall beyond the specification limits, either below the lower specification limit or above the upper specification limit. It's very important that we design processes and operate them in a manner that keeps the total process inside the specification limits all the time. Such a process will be called a capable process. If a process goes as it's operating naturally, if it produces output that goes beyond the upper and lower specification limits, we will say that that particular process is not capable. We'll try to get some quantitative measures of this as we go into this. What does process capability analysis do? It actually focuses on improvement. It tries to improve process capability of a particular process. Any process that you bring about, it will always have some variation. What we have to do is we have to make sure that that variation does not take the output beyond the specification limits. Now, such a process will generally be under the influence of factors which cause too much variation. One of the tasks in process capability analysis is, first of all, to obtain a measure of how good that present as is capability is. If that turns out to be too large, if it turns out that there are parts of the process that are producing output which are going beyond the specification limits, we have to tighten the process. That means we have to go back, and if you look at the process diagram, in this diagram there are these factors A, B and C. Perhaps they have been set in such a way, or perhaps the controls on them are not good enough to keep this process well within the specification limit. When you look at the output of the process, perhaps there are too much variations in these, and perhaps there is too much noise also. These are the reasons why my output may be beyond the specification limits and my process capability may be poor. In trying to measure, in trying to quantify process capability, what we do is we look at the individual output values. So for us, for example, it could be the X1, X2, X3. These are measurements produced that are coming out, that are on the items that are coming off the production line. You measure some quality dimension, which could be distance, it could be length, it could be weight, it could be viscosity, it could be any of these things, any of these characteristics that you can measure. Once you have measured it, you go out there and you compare that quantity. You compare that quantity's value to the tolerance. If it turns out that the measured value is beyond the tolerance, that means you produce something that is off spec, which we call in industry, we call it off spec. Our goal is going to be to try to understand factors that are causing this wide variation in the process and are producing products that are beyond the specification limits. So the process capability studies actually, they really look at the range of the individual outputs. In fact, the output that I show here, these are the plots of the individual items. So I've got various individual items. They've been plotted on this. And it turns out some of those are below the specification limit here on the lower side, and some are beyond the upper specification limit. But these are all individual measurements. I'm not talking about X bar. I'm not talking about R. I'm talking about raw X values. That's what I'm talking about. That's what I've plotted. In fact, that is the quantity that I need to measure in large quantities, large numbers, to try to see what the distribution looks like. If that distribution turns out to be flat and a good chunk of it is beyond the specification limits, I will say that the process is not capable. I cannot go out to the marketplace and compete in the marketplace, in the open marketplace, with a process which is producing products that are generally off-spec and that have a good fraction of its production that is off-spec. In trying to measure process capability, we make an assumption. We assume that the output is going to be normal. Of course, we could work with any other distribution, but the convention has been that we've assumed the output to be normal. In fact, most of the stuff, if you measure them, if you look at measured data generally follows the normal distribution. That just makes our life a little easier when it comes to quantifying process capability. The other thing that we'd also like is, we'd like the process to be under the influence of chance causes only. We do not want the assignable factors to be disturbing the process when I'm trying to make a measurement of process capability. So when I think of measuring process capability, it's very important for us to realize that the process must be under what we call statistical control. That means it is under the influence of chance causes only. Those are small vibrations and so on and so forth. Those are the parts, those are the causes which do not shake the process too much. Any factor, any item, any cause that actually would shake the process, we first have to stabilize the process. We first have to make sure we've removed all the assignable factors. And the way to do that is to run the process under process control using control charts, perhaps the X bar chart or the R chart, and then remove as many of those factors as possible. Once you've done that, what is left is the process that is operating under the influence of chance causes only. So that's like one of the assumptions when we go out and start measuring process capability. Couple of terms we'll be using here. One is, of course, tolerance. And tolerance is the difference between the upper and lower spec limit. And if you look at my diagram here, the specification limit here is denoted by this line there, that is the upper spec limit, and this is the lower spec limit. This range is the tolerance. This range is the tolerance. This actually implies the range of quality characteristic values that the customer is willing to live with. This is rather important for us to realize. We've got to find out what that tolerance is that is given by the customer. The second thing, of course, is the variability. And again, you can notice the variability there. That's a notion of, that's really basically the plotting of all the output that I've measured without controlling anything, without basically doing any kind of screening, any kind of censoring and so on. We just take that raw data and we plot them up completely. And that would reflect now the variability in the process itself. That's also something very important. We've got to remember now, whenever we are dealing with process capability, we are going to be using specification limits, not control limits. So yes, we use control limits to stabilize the process. We use control limits on control charts to try to stabilize the process, which means we want to remove any assignable cause that might be disturbing the process. That is something we'd like to be able to do. But once we've done that, the process capability measurement will in no place utilize control limits. That it will not do. So please do not be confused between these two types of limits. One is specification limits. These basically specify the range or the tolerance that the customer is willing to live with. That is the range of quality characteristics that is acceptable to the customer. On the other hand, if I'm trying to control a process, if I'm trying to do control using statistical process control, I shall be interested in what we call control limits. And then these control limits will be imposed on the two statistical charts. One is the X bar chart and the other is the R chart when I'm making measurements. I could do, of course, the same thing with P chart or C chart, any of those charts. But I use control limits only to stabilize the process, only to bring it under what we call statistical control. All right, let's go on and take a look at the distribution itself. Here's the distribution. And if you remember the normal distribution is symmetric. It's got two parameters controlling it. One is mu, which shows the mean of the process. The other is sigma. Sigma indicates the variability of the process. So there are two aspects of the output here. One is, of course, where is it located centrally? Where is the central location of the process? There is a central point about which the process data are distributed. So that's going to be our mu, the mean. Then, of course, we also have to bring in what we call variability of the process. And the parameter that indicates that very easily is our sigma. Sigma is standard deviation. And if you specify mu and sigma, you've defined everything that you need when it comes to defining a normal distribution. Now, some other features also we utilize now. Once we've acknowledged that the process is going to be normally distributed, we do a couple of things. We can mark parts that will specify the exact area that will fall within a certain range that is beyond, that is above and below the mean value of the thing. If I go 1 sigma beyond mu, that is like this point is now going to be mu plus 1 sigma. And this point is going to be mu minus 1 sigma. This difference here, the distance between these two is 2 sigma. And that covers approximately 68% of production if your output is going to be normally distributed. If it is normally distributed, then within plus sigma and minus sigma, you'll have 68% of production. If you go beyond this, if you go to 2 sigma limit on the right hand side and 2 sigma below the average, below the mean there, that will cover about 95% of the total area that is under the distribution. That is the distribution of the output that is there if the output is normally distributed. If you go to 3 sigma, the range that is covered between mu plus 3 sigma and mu minus 3 sigma, that total area turns out to be 99.7%. So very little is left beyond that. In fact, these turn out to be measures that we utilize when we do our process capability calculations. So something for us to remember is, if the distribution is normal, then within plus and minus 1 sigma, I'll have 68% of output. If I expand that range to plus and minus 2 sigma, I'll have 95% production. That will be in that range, that new range, plus minus 2 sigma. And if I make that tolerance even wider, if I make it 3 sigma, that is, if I go mu plus 3 sigma would be the upper limit and mu minus 3 sigma would be the lower limit, then the amount of output that is inside the plus 3 sigma and minus sigma range, that is going to be 99.7%. This is the property of the normal distribution. This is a property of the normal distribution. And we utilize this when we do our CPK calculations. Take a look at the full range now, the full range that covers almost all the output. Almost all the output is now contained within mu plus 3 sigma and mu minus 3 sigma. This 6 sigma range pretty well covers almost the total output if the output is normally distributed. That's something for us to remember again. And of course, what we do is we go on and we sort of try to see what happens in a real process. Now, if you remember, the best place to put your production is to put the average value right on target. This gives you an accurate process. If your average equals, if the average value of output coincides with the target of the process, that's a requirement, you end up with what we call an accurate process. A precise process is going to be one that's going to have a tight distribution. A precise process always has a tight distribution. And we have some means by which we can specify these different characteristics, accuracy and precision. Let's see how we do that. I have a process here, and this process has a target which is at 5.00. That's the target. The target being there, what we have to do is keep the target there and look at your real output. The real output actually, if I average the whole thing, the real output X double bar, that is at 5.010. Notice the difference between 5.010 and 5.00. This actually indicates there is a problem with accuracy of the process. There's an accuracy, there's some difference between the target and what the average quality characteristic is that the process is delivering. So here the first problem that we have is we have some problem of accuracy. Then of course there is something that I would like to find out from customers, and I say regardless of whatever the process is doing, what are your requirements? Then the customer comes along, he says, well, the target is correct. I want the quality characteristic to have the value of 5.00. My tolerance on the upper side is 5.05 and my tolerance on the lower side is 4.95. And that's going to be my tolerance value. If you supply me output, if you supply me products that are in this range, I'll be pretty happy. Of course, I'll be most happy if you supply it right at the target. But I'll tolerate things that are, I'll accept things that fall within the upper spec limit and the lower spec limit. And this is my tolerance band. This is what the customer conveys to you. Now come back to production. Come back to the process. Remember the process that I showed. I showed you a process when I drew the diagram here. Here's the process. The process is what I'm operating. I as a manufacturer, I'm operating this process. My output may not exactly be fit for the customer to use 100% of the time. Let's take a look at what is happening there. The target has been given as 5.00 and the tolerance band has been given as 4.95 to 5.05. These have come from the customer. When I collect some output data and I plot it, it gives me this dark curve there, which is, you can recognize it's a normal distribution, more or less a normal distribution. And lo and behold, a good chunk of that normal distribution, it falls below the lower specification limit. So this would be called out of specification. These products are going to be out of specification. These would not be acceptable to the customer. If I look at the outside, if I look at beyond the upper spec limit, again I find there's a whole bunch of output there that is again beyond the tolerance of the customer. So again, these are again out of spec. If a lot of my production is like this and this, I cannot compete in the marketplace with a process that is operating like this. And that actually means that the process capability of this process, this blue process or this dark blue process, is not so good, is actually not so good. It turns out that the inherent variability, this is the natural variability of the process, that is wider than the tolerance band. Therefore, in the language of process capability, the process is not capable of taking care of the customer requirements 100%. It is not. Let's take a look at two processes. What is a perfect process? I show the tolerance here, the upper and lower specification limits, and look at the natural variation of the output. It's well within the tolerance. So this is a good process. This is what we call a capable process. It's wholly within the tolerance. The natural variation of this process is wholly within the tolerance. Look at this process by contrast. The tails are beyond the tolerance limits, which actually says if I use this process, to basically supply a marketplace, there will be many occasions when there will be complaints from the customers because I find some tails of it that are beyond the tolerance limits. And this process is therefore not capable. So the green process is capable, but this lower process is not capable. This is just to give you an idea of what we are talking about when we talk of capability. The process to be capable has to be wholly within the tolerance. The same picture is shown here. Now, what do we do? What can we do if we've got a process like this? This is the process that again is, as you can see right away, the lower and upper specification limits are shown, and there are these red tails, which are like unacceptable output. what do? Well, we could redesign the process. We could change those factors A, B, and C. Remember these factors A, B, and C, these are process control factors. Perhaps also there is a lot of noise that's causing the inherent variation. First, we could redesign this process. We could probably redesign this process and bring it wholly within the tolerance limits. And the tolerance limits, as I indicated to you, those are shown right there. So that could be done by redesigning the process. That would be one strategy. Suppose this was a machine that was like an old machine and there is no way I can redesign, I can fix the machine, then of course I'll have to go for alternate process. That's like another option, that's option number 2. That's also a possibility if I'm going to be competing in the same marketplace. That's also going to be one of my requirements. I shall be using an alternate process to supply to this marketplace. The third approach is going to be, why don't I produce the way I produce? But I sort the output between good and bad. What I do is I make some deliberate inspection. I inspect everything that comes out of the process and I reject the parts from shipment that are either below the lower specification limits or above the upper specification limits. I supply parts or I supply products that only fall within the tolerance band, and I throw away the parts, perhaps I scrap the part or I rework the parts that are beyond the spec limits. That's going to be expensive again. And the other thing, of course, is I go and plead with the customer, please widen your tolerance band. Please widen your tolerance band. If I did that with the process that I have here, if the customer was kind enough, if you'd widen the tolerance band, then these red areas would reduce in size. That could be my fourth strategy. It's certainly not a good strategy at all. The best strategy is really to redesign the process. And that means you have to identify factors which are causing this wide variability. Let's now see how we measure process capability, how we end up quantifying process capability. Process capability is defined as follows. It is CP. CP is the notation that is used. CP is the notation. CP is called process capability ratio. It's a simple measurement of process capability. There are other measurements that are more complicated than this, but this is the simplest one. It's used a lot by industry. CP is just the ratio of specification width, which is a tolerance, divided by process width, which is 6 sigma. So I've got CP equal to upper spec limit minus lower spec limit, that is the tolerance given by the customer, divided by 6 sigma. And this sigma is my process variability. Remember, I had process variability. I'm just going to bring that up again. I'm going to bring up, this is my, notice here the 6 sigma limit there. This is my process variability. So this would be my denominator. When I look at my CPK formula, my CP formula gives me 6 sigma in the denominator. I've got tolerance up near the numerator, and I've got in the denominator, I've got 6 sigma. This ratio will be called CP. It turns out if your process is a 6 sigma process, then your process has such good precision and your centering is so good that this CP number turns out to be 2 for your process. Let me give you 1 or 2 other examples. Suppose you have a tolerance limit that fits exactly the 6 sigma quantity. So what we have here, if I would write the formula there, I have CP equal to, and I put down here upper spec limit minus lower spec limit divided by 6 sigma. And suppose this sigma was exactly equal to this, then I'll end up with upper spec limit minus lower spec limit divided by upper spec limit minus lower spec limit. And this turns out to be a very neat formula. This gives me a CP equal to 1. Now this is the process for the tolerance and the distribution of the process, they match exactly. This process has a CP equal to 1. Is this a safe process? It's not a very safe process, because there are chances that occasionally you will end up with some parts that are beyond the specification limit. For this, what we have to do is we have to make this tighter. So we should, in fact, strive to get a process. We should understand the causes of variation. We should try to strive to get a process that is wholly within the limits like this. So there is some room here, and also there is some room here. So there's no real danger of going beyond the control, beyond the specification limit. I have the upper specification limit here, upper specification limit there, and lower specification limit there. Those are that's my tolerance band. This is my tolerance band. And of course, then within that, my good process is such that it's got some slack left on both sides, so that this one is really, it has hardly any chance of going beyond these lower and upper specification limits. In Motorola's case, when they reached when they produced a process that had the 6 sigma quality, that means it produced parts that was only 3 or 4 parts per million. Their CP measure turns out to be 2. Again, look at the idea of process capability. What are my design specifications? Design specifications are basically determined by what the customer requires. So I've got my upper specification limit there and lower specification limit there. If the process is centered, if the process is not capable of taking care of meeting these requirements, I'll have some of these parts of these tails that would be beyond the specification limits. And if a process fits exactly within, we say the process is capable. It has a CP at least equal to 1. Hopefully, it should have a CP that is more than 1. More than 1 is always better, and certainly below 1 is not acceptable. Look at a process here. There are 2 processes. They have 2 different types of problems there. Both actually are pretty tight processes. This one is a pretty tight process, as you can see. This one also is not a very poor process in terms of precision. But this process is centered. No real problem there. And it is totally capable. This process here, although the variation is not too wide, it is off to one side, and therefore it does have some parts that would be colored red. This part here, this part here, this tail here would be colored red. What we have to then do is, first of all, just the old measure of CP. Remember, I have the old measure of CP, which I showed here. I used a formula that was upper spec limit minus lower spec limit divided by 6 sigma. Notice this formula does not incorporate the target anywhere. This formula does not incorporate the target. It has variability sigma, but it does not in any place bring in mu. Therefore, this index is not capable of detecting a problem which is like the lower part of the problem here. Like, for example, this lower part of the problem. This problem will not be detected if you measured your process capability using CP only. What do we do then? Well, we have to modify the measure of CP. We have to change the formula. That formula is changed from CP to what we call CPK. It's called Process Capability Index. And that will be done where I'll be bringing in mu as well into the formula. Let's see how we do that. The definition of CP was tolerance range divided by process range, which was the upper specification limit minus lower specification limit divided by 6 sigma. That's all. That is all that was CP. What we do is we change that. And here's just an example of how you do the calculation. Let's say that I'm weighing certain things and the weight of the object. The weight of the object is such that I have what we call a specification limit on it. And the specification limit is 9 ounces plus or minus half an ounce. So 9.5 ounce to 8.5 ounce, that is actually the tolerance of the customer. That is my range of specification. If the process mean turns out to be 8.80, let's say that I just keep a note of that. And what we've done is we basically looked at the quantity which is here. I have here specification limits, which is 9.5 minus 8.5 divided by 6 times sigma. Sigma is also given here. So in trying to find CP, I've never used my mean. I've never used the mean. I only use specification limit and my sigma value. And that turns out to be 9.5 minus 8.5 divided by 6 times 0.12, and that turns out to be 1.39. Now you may think this is pretty good. because this CP value is greater than 1, which is saying there should be no tail ends, no red tails. But the problem is this, my process itself is not centered. This is not coming at 9.0, this is at 8.80. So there is a displacement of the average process. There is a displacement of the average process, and if I show you the diagram corresponding to it, it's more like this. It's more like this. I have a tolerance standard target, but the average turns out to be somewhere else. And that's not such a good idea. That's not such a good situation to have. Let's see what we do. Perhaps what we should do is, instead of misleading management by calculating only CP, we got to convey to them, look, gentlemen, there is a difference between the process mean that is being delivered by the process and what we consider to be okay, that is the target, that is really the best value of the quality characteristic that is required by the customer. To do this, what we do is, we change the formula. We calculate process capability now using a different formula, which is X double bar. What is X double bar? It is the grand average of all the data values that I've collected at the output. X double bar, like in the old control chart situation, it is the average of all the Xi values, X1, X2, X3, X4 and so on. So you could have X200. You take you collapse all of them, compute one average. That is this X double bar. This is the overall process average. This indicates the midpoint of the distribution of the output. That's what I've used here. This CPK formula has two parts. One is going to be X double bar minus the lower specification limit divided by 3 sigma. Sigma is still our old process standard deviation, comma, upper specification limit minus X double bar divided by 3 sigma. And notice here, CPK is the minimum of this quantity or this quantity. Whichever turns out to be nearer to the specification limit, either because it is too close to the lower specification limit or too close to the upper specification limit, I'll have a smaller quantity there. And that's going to reduce the value of CPK. And if I show you a calculation, here's a little calculation. I use the same data that we had before. My tolerances were given as 9.0 plus or minus 0.5 ounce. Process mean, this is the X double bar, turned out to be 8.80 by actual measurement. Process standard deviation turns out to be sigma, which is 0.12 ounces. And this I found by calculating my R bar by D2. Remember this is what we also used in one of the earlier calculations when we were doing SPC. Now we bring in the CPK formula. This is different from the CP formula. CPK formula is minimum of X double bar minus lower specification limit divided by 3 sigma, or the upper specification limit minus X double bar divided by 3 sigma. And that's exactly what I find here. Now what is X double bar? This quantity is X double bar. 8.80 is X double bar. So what I do is, I come out here and I plug in the right numbers. I plug in X double bar minus lower specification limit, which is 8.50. Divide that by 3 times sigma. That's like one quantity. The other is 9.5, which is actually the upper specification limit, minus X double bar, which is 8.80. Divide by again 3 times sigma. The lower of these two is 0.83, and this is definitely less than 1, which indicates to me that part of this tail of production is perhaps beyond one of the specification limits. It's probably beyond one of the specification limits, and that's bad news. That means this process again is not capable. So notice the difference in going from CP to CPK. CP basically looks at the overall variability of the process. CPK looks at the centrality of the process. CPK worries about the displacement of the overall average from the target value. That's what CPK does. So CPK turns out to be a better value for measuring process capability. Now here are some scenarios. If a process fits in exactly within the specification limit, the value of CPK is going to be 1. If it is well within that, my value of CPK could be 1.10. If it's really well within the specification limits, CPK value may rise to 3.0, and this is a really capable process. no customer ever will be unhappy with this process. In fact, they'll be pretty happy even here. Then of course, I've got CPK equal to 1, even if there is slight displacement. There is some slight displacement, but the curves are, the distribution still wholly contained within the spec range. And therefore, this CPK turns out to be 1.0. If there is a displacement of x double bar from the target value there, unfortunately, you cannot see them because those have been erased from this picture there, but x double bar stands here and your target value stands there. There is a difference between those two. So this process lacks accuracy, and look at the tail, it has fallen out. Same thing with this. Even if this process is narrower, it's tighter than the process here, still CPK is poor. So it turns out that the best situation to be in is to be well within the tolerance limits, of course, number one. Number two, the average has to be pretty close to the target. If that is there, your process is very capable. And this could be measured using this CPK, process capability index. How do we improve it? There are a couple of ways to do it. Suppose your process had the distribution that was like the red dotted line. This was the distribution of the output that you had coming out of your system, your machine, or whatever it was. It was producing output that had this kind of distribution. The spec limits are shown here, and notice carefully that some tail of the old process is below the specification limit and also above the specification limit. This process is clearly not capable, and the CPK measure here turns out to be 0.766, which is less than 1. I can improve this process, and here I can do that because centrality is not an issue. The old process also is really right on target. The average x double bar is standing right at the target, no issue there. But if I make the process tighter, that means if I reduce sigma, I can go from that green line to this red line, which also is not quite perfect yet because it has still got a little bit of tail there. But certainly CPK has improved from 0.766 to 0.9544. This is the better process, clearly. It will have very few rejects. The other way to try to improve a process that has got poor capability is to shift the mean. If the mean was off target, if you adjust your factors in such a way that the average of the process shifts and becomes coincident with the what we call the target of the process, which is what has been said by doing some market research. It turns out you'll have a larger area of your process that will come within the tolerance limits, and again process capability will improve. The old process capability with the off-centered process was 0.699, and the new process with your x double bar shifted to coincide with your what we call the target value. That CPK turns out to be 0.766, which is larger than 0.699. Therefore, there has been an improvement in the process. And this improvement we have achieved by shifting the mean of the process. The red line, the red curve was shifted to this yellowish curve there. And that's how you end up with improving the process. Now there is a process capability index that goes even beyond this, and this one is called PPK. There is no real difference between what we've done before with our CPK and PPK. PPK basically looks at process performance. It looks at process performance. The only difference in the formula between PPK and CPK is, look at the denominator. The denominator of PPK is 3S, sample standard deviation. The denominator in the other case, I'm just going to go back there, CPK, the denominator of CPK was 3 sigma, and this sigma was found by this R bar by D2, which is really the process standard deviation. There is one thing called process standard deviation, then there is something called sample standard deviation, which is a local standard deviation. If you do that, you end up producing, use the same formula, you end up producing a process capability index that is called PPK. This PPK turns out to be another measure, another process capability measure, which is also utilized. Let's now do a little broad review of what we've done so far. Every process displays some variability. Some may be normal, some may be abnormal. So notice here, I have a process here which is controlled by some control factors. These are process control factors. It's also influenced by these noise factors. The result is this variation. This is something that will happen in every process. And it turns out some of this variation would be normal and some of it would be abnormal. In order for us to what we call get an assessment of the capability of the process, that is how good the process is in meeting customer requirements, we have to come up with an index that is called process capability. And there are a couple of ways to measure that. One is, of course, you worry just about the spread of the process. You don't worry about the centrality of the process. In that case, you'd be using this quantity called CP. If you use CP, you end up with a simple formula. And this just basically gives you an idea what is the chance of my producing something that's going to be within these specification limits, because my process is pretty tight. This does not, CP by itself does not worry about the centrality of the process. If you're worried about is there some way I could get an idea of how good my process is, how poor my process is, look at your control chart. If there are a lot of points, a lot of statistical points, these are the X bar values or the R values. If they are beyond the control limits, clearly it's not very likely that your process is capable. This is something you've got to worry about. So if you're starting out trying to control a process, of course you could produce a histogram of the output and you could do that. But it would be a better idea to try to run a control chart and take a look at whether there are many assignable causes that are also impacting the process control chart, the process. If the process is being influenced by a lot of these what we call abnormal causes or assignable causes, spend some time to try to remove them. Once you've removed them, what is left is just the chance causes. These are the random factors that will be there no matter what, unless you improve the technology of the process. If you improve the technology, you can of course tighten up the process. That's like one great way to try to improve a process. So control charts would be a pretty decent place to begin your study, and take a look at just in case these charts show some sort of abnormal variability. It's possible that control charts would give you false signals. It's very possible that the variation that you see is normal. But remember alpha error. Alpha error is the type 1 error committed with a control chart, which says I get a signal. That means I see a point beyond what we call control limits, upper and lower control limits on a control chart. And I go witch hunting. I try to sort of diagnose the process. I go back to my process and I start taking a look at all these different factors to try to see, is there something wrong with A? Is there something wrong with B? Is there something wrong with C? Let's investigate a little bit more to try to sort of see, can we remove something there? Suppose the process was not disturbed. It was just statistical variation that led to that condition there. You'll end up with a process, you end up needlessly troubleshooting the process. So that can happen because the control chart, there's a teeny weeny chance, 3 or 4 parts per thousand, 3 or 4 data points per thousand, when the chart itself may give you a false signal. That is there. And this is the type 1 error. If we do now what we call in control, if we remove assignable causes, and what we are left with is essentially the process under the influence of chance causes only, which is the natural variation of the process. It is at that point you should try to make an assessment of what we call process capability. Process capability is the capability of the process to be able to just basically produce any output. It will meet customer requirements. It's wholly within the tolerance that is tolerated by the customer. If there is a process like that, you have nothing to worry about. I should of course caution you that many times the range of the process, that means the difference between the maximum value of the output produced and the minimum value, it may be pretty tight, but the overall process itself may be off spec. And that is because sometimes the average, which is XW bar, may not coincide with the target mu. If XW bar and mu, if they're different from each other, This will cause some part of the process to go beyond the control limits, even if the process has decent distribution, as we saw in one of the earlier curves. So what we have to do is we have to do two things now. The first thing is get an idea of process variability, which you could do just using CP. Plot some charts, try to make sure that there are no assignable causes present in the process that disturb the process. This is something you have to do. The third thing you have to do is compute CPK. And CPK will tell you if there is a problem of basically positioning the process, which means is it running right now with the average quantities, average quality characteristics being produced that are beyond what we call either below or above the target that is desired by the customer. If it is off target, that means there is a problem with the process there. I have to do some adjustment to try to make sure the average returns to the target value. Then I've got the best process. Then of course I've got to tighten up the process. The methods for doing this, some of this can be done through experience, but a better way to do this is to apply design of experiments. Use factors, and those factors eventually will end up tackling your process there. And they will come up with those factors that really cause either a shift in mean or a shift in sigma. That can be done by picking the right response, making the right measurements, and conducting experiments in the framework of what we call a matrix. If you do those matrix experiments, you are very likely to discover the main effect of the different factors that are there, the process control factors, and also their interaction. Once that is there, once these variations have been located, you've got not much to worry about. All you have to do is adjust the process, adjust the settings of those factors, the factors that turn out to be the culprits. You adjust them in the right direction, the process will restore, the average will come back, X double bar will come back to target, and also sigma will reduce. The overall variance of the process will reduce. This is something that we need to do. This is a very interesting area. In fact, design very often aims at simplifying. It looks at simpler parts, fewer parts, and so on and so forth. Always the idea is to try to come up with a process which has got easy to operate, easy to assemble, easy to produce, and any chance of making a human error, those also have been reduced. Those have been minimized. You look at the causes of variation. You monitor the process using a control chart. You look at the output. If it turns out that you've got a lot of assignable factors there, then of course you go back there, do an investigation there. If you've taken care of the assignable factors, then you look at the spread of the process. Because that is now the natural variation of the process. If that goes either above or below what we call the tolerance, you have to then adjust, you have to then play with the sigma of the process. And this again, like I said, it can be done. This is the overall variability of the process. And one great way to tackle that is to apply design of experiments. So we wrap up this session by saying if there is a process that is influenced by many factors, I can monitor it using process control charts. And then of course I've got this tool called CP or CPK measurement. These give you a pretty decent idea. See, the process control charts themselves, they don't talk about specification. But the moment you bring in CP or CPK, you're talking specification. And now you're talking about what is of interest to the customer, to the final user. If you do this, your process will stay in control. Also, it will consistently produce output that is well within the tolerance that is tolerated by the customer. We'll continue our series with the next lecture. Thank you very much.